Okay, so in the previous class, we have gone through the different electrical properties of germanium and silicon, and how the mobilities are going to defined in case of a semiconductor that is having two different charge carriers. And also we have seen mass action law. So next topic is like we are going to have different charge carriers in the condition of a magnetic field. Like we are putting the charge carriers in a magnetic field, then what will be the effect of that magnetic field on the charge carriers? We will analyze. So that effect is basically analyzed by the Hall, that is experimentally verified. So that experimental effect is called Hall effect. Okay, so we will see that. So basically in Hall effect, it states that if any specimen is there, like a metal is there or a semiconductor is there, if this metal or semiconductor that is in rectangular shape, okay, that is other that could be a square type or it should be a rectangular type. Okay, so if it is placed such that uh, in z direction we are having the magnetic field, okay, and the current is flowing in the x direction, so this is the direction of current, then the charge carriers available in this metal or a semiconductor, these charge carriers will be experiencing a force, and that force will be downward side, like it will be in negative y direction. So the force will be in negative y direction. So this effect is called Hall effect. Okay, so we have placed a semiconductor or a metal that is having a width w, and d is the height of the semiconductor or metal that is a specimen, and it is placed such that the magnetic field is in z direction, positive z direction, and the direction of current is in positive x direction. Then the force experienced on the charge carriers, so the charge carriers will be either electron or holes in case of semiconductor, and the charge carrier in case of metals that will be electrons. So the charge carriers will be experiencing a force that will be making it to a downward. So this force will be nothing but because of the induced electric field. So that means here in Hall effect, electric field will be induced. So that how this electric field is induced, we will see that, and what are the different applications of this Hall effect. We will also see like how this Hall effect is going to determine different parameters. So we will just write what is Hall effect. So Hall effect is uh, if a specimen that is a metal or a semiconductor which is carrying a current I. If the I current is carried by the specimen which is placed in transverse magnetic field, that is P, then an electric field E will be induced. Basically then an electric field E is induced in the in the direction in the direction perpendicular to I and that is current and magnetic field. So here the direction of the field will be in the opposite y direction, and that will be perpendicular to the magnetic field as well as the current direction. So here we have assumed like this is the surface, one of the surface of the semiconductor or metal, that is a specimen we have placed. This is suppose surface 2, and the downward surface is we have to consider is like 1. Then based on the potential across the surface 1 and 2, uh, different parameters will be defined. So basically, once we have done this experiment, some observations will be uh, obtained, and based on that observation we are going to find some parameters. Okay, so by using Hall effect we can measure different parameters. So we just note it down. We are like Hall effect is used to measure. So there are different parameters we can measure. So first is like we can measure whether this specimen is a metal or a N-type semiconductor or a P-type semiconductor. Okay, so based on the experiment, uh, whatever this Hall effect is going to do with this specimen, we can measure whether this specimen is a metal or N-type semiconductor or a P-type semiconductor. Okay. Also, we can measure the carrier concentration. So, what is the charge carriers available here? Electron and holes are there. What is the concentration of this charge carriers? We can measure that also. Third is like we can measure what is the mobility. So the charge carriers are there. So what is the mobility of these charge carriers? We can also measure that. Okay, and also we can measure the magnetic flux density. So based on the experiment, we can measure the magnetic flux density, and also in some cases like in case of electromagnetic wave transmission, we can measure signal power. So in case of EM wave case, we can find out what is the signal power by using this experiment. Okay, so we will just see like how we can measure whether it is uh, a N-type semiconductor or a P-type semiconductor. Okay, so in all these cases we have seen like B is in Z direction, current is in X direction, and in negative Y direction we are having the induced force or force exerted on the charge carriers basically. So here, suppose this current that is flowing through this specimen, that is flowing from basically from this side to this side, that means in positive X direction. That means if current is flowing from left to right, okay, so if current is flowing from left to right, then because this current would be because of the holes and electrons also. Okay, so if current is flowing, current direction is from left to right, so this current would be because of holes. So holes will be in the direct will be flowing in the direction of uh, current only. So holes will be flowing from left to right, and this current will be because of the electrons also, but in that case electron will be moving from right to left. Okay, so electron will be moving from right to left. So this is the movement of holes and electrons in this metal or the semiconductor, whatever specimen is there. So once it is moving, the charge carriers are moving. If the holes are moving or the electrons are moving, suppose it is electrons that is moving. So in that case, if the electrons are moving, okay. So if electron is the only, or you can say the majority of charge carriers is electrons is the free charge carrier constituting the current. Then if the force is exerted because of the Hall effect, all the electrons will be moving towards the surface 1. So this is the surface 1. So as the this specimen is having holes as well as electrons, but current is moving, current is flowing because of the electron. If that is the case, then all the electrons will be going to the surface 1 because of the force induced on on the charge carriers basically. Okay, so here if the electron is the charge carrier, then force will be making it to move to the surface 1. If the electrons are accumulating near this surface or on this surface 1, then the surface 1 will be negatively charged with respect to the surface 2. Okay, so if electrons is the case, so we can just see like in n type of semiconductor, the semiconductor is n type semiconductor. In that case, current will be basically because of the electron movement. Okay, so if electron movement is there, and because of the Hall effect, it will be experiencing a force. So the electron will be accumulated to surface 1. Okay, so electron movement constitute the current in n-type semiconductor. Basically the majority of charge carriers is electron in n-type semiconductor. So in that case, because of the Hall effect, electron will be accumulated to the surface 1. So if electron is accumulated to surface 1, surface 1 will be negatively charged, and we can say, and surface 2 will be positively charged. Okay, so if this is the case, so if the surface 1 is negatively charged and surface 2 will be positively charged, that means the two surfaces will be having a potential difference. Okay, so as this potential difference will be generated between surface 1 and surface 2, there will be an induced voltage. Okay, it will be resulting an induced voltage. So this induced voltage will be called as this induced voltage is basically the Hall voltage, we can call it, like it is because of the Hall effect. So this voltage will be induced because of the Hall voltage. So this induced voltage is called Hall voltage, it is VH. So because of the induced voltage, what is the sign of induced voltage, whether it is positive or negative? Based on that, we can say whether the specimen is an n-type semiconductor or a p-type semiconductor. Okay, so this Hall voltage will be defining the uh, specimen category, whether it is metal, semiconductor, or in semiconductor whether it is n type or p type. Okay, so this is how experimentally we are able to find out the Hall voltage, and this Hall voltage magnitude, whether it is positive or negative, is going to define whether the semiconductor or the metal is a n type or p type. Okay, if it is metal, uh, in that case Hall voltage will be negative. Okay, so the VH in case of n type, VH Hall voltage will be negative, and in case of metal also, because in n type and metal the charge carriers or majority charge carriers are because of the electrons only, so the Hall voltage will be negative. But in case of p type of semiconductor, the charge carriers will be holes. Okay, so the holes in that case, in case of p type, the holes will be the charge major charge carriers. So once the holes are the major charge carriers, it will be experiencing the force, so the holes will be accumulating to the surface 1, and once the holes are going to accumulate on the surface 1, the surface 1 will become positively charged. Okay, so that will be creating this induced voltage, Hall voltage, that will be a positive. Okay, so based on the nature of this Hall voltage, we can find out whether it n type or p type or a metal. Even that, in one of the cases, like if Hall voltage is 0, if Hall voltage is 0, what will the condition? What it indicates? If Hall voltage is 0, it will be indicating that the semiconductor is an intrinsic semiconductor, or we can call like this specimen. We can note like specimen that we are using is an intrinsic type of semiconductor if Hall voltage is a 0. Okay, so this is one of the, you can say, important case. It can be asked directly in the objective type of questions, and even based on the Hall voltage, we can have this criteria. So based on the Hall voltage, we can categorize the semiconductor or metal case, whether it is n type or p type. So in that objective type questions also, it can be asked directly. Okay, so this is how we will be defining whether it is semiconductor or metal. In case of n type, in case of p type semiconductor, it will be just opposite to the n type that we have discussed. So here in p type, holes are the majority carriers. So if holes are the majority carriers constituting the current, okay, so when we are placing this holes into the condition of magnetic field, and here current direction is in positive x direction and magnetic field is in positive z direction, then the force experienced will be such that the holes is going to be uh, forced downside, that means to the surface 1. So force will be the holes will be the majority charge carriers, so it will be forced because of the Hall effect. It will be experiencing a force in negative y direction. This will result surface 1 becomes positively charged. Okay, so one alternate case we can see, suppose holes in p type, suppose in p type, uh, suppose if it is a p type of semiconductor, if this, suppose in p type also the current is constituted, if this is the current direction. So in p type, suppose the electrons are resulting in the current flow. Suppose electrons are the majority carriers. Suppose we are supposing like electrons are majority carriers. So the electrons will be moving in opposite direction. Like this is the direction of current. So electron will be moving in this direction. Okay, to constitute the current. If this is the case, suppose we have an electron. So if this is the case, if we are placing this p-type semiconductor into the condition of Hall condition, like Hall effect is going to be in uh, put on this p-type semiconductor. If Hall effect is going to be put, if electrons is the majority carriers in p-type, then on the surface 1, the surface 1 should be negatively charged and surface 2 should be positively charged. Okay, if electrons are the majority carriers in p-type, but experimentally has been found like this is not the case. Okay, experimentally by using Hall effect, it has been observed that the surface 1 is positively charged and surface 2 is negatively charged. Okay, so this states that the holes, that is one of the uh, charge carrier that constitute the current, is positive in nature. Okay, so holes are positive in nature. We can experimentally verify by using the Hall effect. Okay, so if holes are not positively charged in nature, then by using Hall effect, that whatever charge carriers are there, the surface 1 should have been negatively charged. But if experimentally it has been found that the surface 1 is positively charged, and that positively charged because of the accumulation of holes on the surface 1, so that's why the holes are equivalent to a positively charged, like electrons are negatively charged, so holes are found to be a positively charged carrier. Okay, so this has been observed by this Hall effect. Okay, so just we can summarize this point, like suppose if surface 1 is there, surface 2 is there. If surface 1 is negatively charged and surface 2 is positively charged, then this will be resulting in n type of semiconductor. So in that case, it is n type of semiconductor, or it could be a metal also. If it is a metal, then also the charge carriers, majority charge carriers will be electrons, so that will be accumulated on the surface 1. That's why it is either n type semiconductor or a metal. If surface 1 is positively charged and surface 2 is negatively charged, it will be a p type semiconductor. Okay, so these are the points we can define whether a specimen is n type or a p type semiconductor is there. Okay, the next point we will see. Okay, so we have started this Hall effect like because of the charge carrier accumulation on the surface 1 and surface 2, there is an induced voltage. Okay, so that induced voltage results in the electric field. Okay, so we have induced voltage that is called hall voltage, that is represented by VH. Okay, so because of this hall voltage and this voltage that has been induced is across the D, that D space, that is the spacing between surface 1 and surface 2. So this is the D is the spacing between the surface 1 and surface 2, and VH is the induced voltage or the hall voltage. So once a voltage is uh, voltage difference is there, and that is uh, separated by a distance D, then there will be an induced electric field. So this induced electric field will be VH divided by T. So that will be volt per meter will be the unit. Okay, so this is the induced electric field. Okay, so because of the induced voltage there will be an induced electric field, and this induced electric field will be experiencing the force. Okay, so if this is the case, that is going to induce the force. So basically here we can write like at equilibrium the induced this E, that is electric field, due to the Hall effect, uh, must experience or must exert a force on the charge carriers, which is just balancing the magnetic force. Okay, so we have applied the charge carriers in the magnetic field. We have placed the charge carriers into the magnetic field. So magnetic field will be experiencing a force on the charge carriers, so that magnetic force will be equivalent to the force exerted by this electric field. Okay, so at equilibrium that will be the condition. So that condition is given like the force because of the electric field is Q into E, that will be equal to the force because of the magnetic field. So here P Q into VD, this is drift velocity. So this is the condition like at equilibrium the electric field induced force is equal to the magnetic force. Okay, so that will be concerned in Hall effect. So this is the condition. Okay, but here we know like electric field is given by VH by D. Okay, so and also we know like this is J, that is a current density. So this current density we have already seen. So the current density in terms of rho is there, that is called charge density. So this is charge density and this is current density. So the current density is related to charge density and drift velocity, and this is equal to I by W into D. Okay, so by putting these conditions we can just find out like this VH will be electric field multiplied by D. This is nothing but we can find out the value of electric field from here. So like QQ will be cancelled out, it will be B. Okay, uh, BD into VD, and we can put this value VD in terms of current W and D and rho. So from there we can see that is B J D by rho or B I by rho W. So here all voltage will be given by Bi rho W. So if we have been given this B magnetic field current and charge density and W, we can find out the V value, that is velocity value, or sorry, this Hall voltage. So once we have find out the Hall voltage, we can check whether this Hall voltage is positive or negative. Based on that, we can define the nature of the specimen. Okay. Also, one parameter is called Hall coefficient. Hall coefficient, that is represented by RH. So this RH is equals to 1 by rho. Okay, so RH is equals to 1 by rho. So by putting this, we can find out like VH will be equivalent to RH, that is Hall coefficient, into BI by W. Okay, so we can relate like Hall voltage is directly proportional to Hall coefficient. Okay, one of the next uh, conclusion from the Hall experiment is we can find the mobility. So here it has been experimentally found from the Hall effect, experimentally found that mu is related with the Hall coefficient and the sigma by 8 by 3 pi into sigma RH. So this has been experimentally found by using the Hall effect, where the sigma is your conductivity. Okay, so conductivity of the specimen, whatever specimen we have used, and conductivity of specimen, and this 8 by 3 pi is sometimes considered as 1, equivalent to 1. So mu is equivalent to sigma RH. This is the relation. So if we know the Hall coefficient and sigma, we can find out the mu, that is mobility. Okay, so based on these, the numerical questions can be asked. Okay, so here we are able to find out the mobility and charge density rho. We are able to find out, that means charge density is nothing but the carrier concentration. Charge density is carrier concentration. Okay, so we can find out the mobility, uh, carrier concentration, and the type of specimen, whether it is p type or n type or a metal. Okay, so these are the different uses of Hall effect. Also we will be summarizing like some points. We can see like where this Hall effect is used. So in terms of applications, we can note it like, so there are some applications. So one is like in magnetic field meter. One of the experiment is like the magnetic field meter. Another one is Hall effect multiplier. So a multiplier can be implemented by using this Hall effect. So that we will see just as how we are able to analyze or design a multiplier by using Hall effect. So basically in a magnetic field meter, this is an uh, uh, instrument that is operating on the principle of Hall effect, and it is basically used for the measurement of magnetic flux. So magnetic flux is basically the B, that is magnetic flux intensity or magnetic flux density, we call it magnetic flux density, and that we can measure by using the Hall effect. So here, if B is the magnetic flux density, so magnetic flux density and magnetic flux intensity. So magnetic flux intensity is H, that is directly proportional to B. So either we can find the magnetic flux density or magnetic flux intensity. So once we are able to find out B, we can find out H also, that is directly proportional. So by using the Hall effect, we can find out B. So this Hall effect concept can be used in magnetic field meters. And what is Hall effect multiplier? So here Hall effect multiplier is like we are basically here applying two uh, inputs. So multiplying means one input 1 is being multiplied by input 2, and that will be your output. So output will be the multiplication of input 1 and input 2. Okay, so once we are providing one input and second input, and the output, at the output we are able to multiply these two, we will be saying like the Hall effect can be used in application where multiplication is required. Okay, so basically here the inputs, two inputs will be like, the first input will be the input that will be in the form of current. So here we are able to find out the first input as the current. If current is the input, first input is in the form of current, and the second input is in the form of magnetic flux density. So the second one is in the form of magnetic flux density, that is B, magnetic flux. So we are applying two different inputs, one is in the form of current and another one is in the form of magnetic flux density. Then the induced Hall voltage, so the induced Hall voltage, that is because of the Hall effect, is directly proportional to the product of these two. Okay, these two signals, hence we can say the multiplication has been done. So here we see the Hall voltage, this is the Hall voltage. So this Hall voltage is directly proportional to B and I, that is the two different inputs. So here, so Hall voltage is having a directly proportional relation with the product of B and I. So we can see like we can implement a multiplier of two input signals B and I, such that the product of two input signal will be directly proportional to Hall voltage. So once we know the Hall voltage, we will be saying like we have obtained the multiplication. So these are the two different applications where we can use this Hall effect concept. Okay, so this is all about the Hall effect. We will just see some questions like how we can implement this concept in the form of an application, like how it will be used. One more point we can see, like if we have charge density that is rho. So this is basically charge density rho is charge multiplied by the charge concentration. So first of all, the concentration of the charge, what is charge, whether it is N or P. Okay, so based on that, the concentration of the charge we will be having, and that will be multiplied by the charge, will be giving you out the charge density. So this charge density will be in the form of coulomb per meter cube. So this will be the unit. So we have defined a term Hall coefficient. that is RH, that was equals to 1 by rho. Okay, so from here we can see like the Hall coefficient will be 1 upon the charge multiplied by charge concentration. So its unit will be meter square per coulomb in case of uh, Hall coefficient. And also we know like the VH Hall voltage is directly equal to RH, that is Hall coefficient. So we know like if we have the voltage, okay, so if we have a voltage and this voltage Hall voltage is negative, then we know the specimen will be either n-type or a metal. And if VH is positive, we will be saying like the specimen is of p-type. Okay, so the similar concept can be implemented because VH is directly to RH. So if we are having the RH, then also we can determine whether the specimen is of what category. So here, so based on the RH value also we can conclude the similar points. Okay, so if RH value is there, that is negative, we can say it could be a metal. Again, if it is metal, it is negative, it can be of n-type semiconductor. And if it is positive, we can say this could be a p-type semiconductor. But the special case was like in case of intrinsic semiconductor, the RH will be very large, very large. Like in case of VH, it was a 0 uh, carrier concentration. Basically in case of RH, carrier concentration will be very small, so that's why the RH should be very large. Okay, so in intrinsic semiconductors, in case of RH, in case of intrinsic semiconductor, the RH value is very large. Okay, so this is the opposite in case of the voltage. Hall voltage is the Hall voltage case was there. Okay, so there are different conclusions that we can make. So now we will see some questions like how we can find out based on the given conditions. Suppose uh, some questions we can see, yes. So suppose one of the question is we are having a doped semiconductor which is having a Hall coefficient. So Hall coefficient is given like the RH is given 3.6 into 10 to the power minus 4 meter cube per coulomb, and the resistivity, that is rho, is given 9 into 10 to the power minus 3 ohm meter. So here in a semiconductor, this is the conditions given. You need to consider like it is having a single charge carrier. It is having a single charge carrier, a doped semiconductor with single charge carrier. We need to find mobility and density of charge carrier. This is the doped semiconductor with single charge carrier, and for that, this is the given condition. We need to find the mobility and charge density. We need to find out the mobility and charge density. So here charge density or density of charge means the carrier concentration basically. So this charge density is nothing but the carrier concentration. We need to find out the carrier concentration. Okay. So this is the two cases that is given. RH and rho is given. So from there we can have the relation. We need to find out the mobility. So mobility, for mobility, mu is equals to 8 by 3 pi sigma into RH. So for general simple calculation, an approximate value of mu can be like, we can replace this 8 by 3 pi as 1. So this mu will be sigma RH. Okay. So this mu will be sigma is equals to 1 by rho into RH. Okay. So rho is given and RH value is also given. So by putting these two, we can get 3.6 into 10 to the power minus 4 divided by 9 into 10 to the power minus 3. So from there we can find out the mobility. So this mu is coming out to be 0.04 meter cube per volt second. So once we know the mobility, the next we need to find out like the charge carrier concentration. So RH is given, and this RH is 1 by charge into carrier concentration or charge concentration. So this charge is given by the Q into the carrier concentration. So this carrier concentration holes could be a hole or an electron, but in the question it is given like it is a single charge carrier. It is having a single charge carrier. That means we can consider it as an N or any single charge carrier. Only one charge carrier we will be considering. So this charge carrier or the carrier concentration will be given by 1 upon Q into RH. Okay. So from there we can find, so Q is 1.6 into 10 power minus 19 into RH. So RH is given 3.6 into 10 power minus 4. So from there we can find like it is 10 power minus 23 divided by 1.6 into 3.6. So the carrier concentration from there is coming out to be 1.73 into 10 to the power 23 per meter cube. Okay. So this is how we will be concluding, and we will be using different relations between the coefficient, Hall coefficient, and carrier concentration, and the mobility we can find out, and we can find out the carrier concentration. One direct method to find out this is like a conductivity we already know. So conductivity, that is sigma, is given as the N Q into mu. This N is nothing but the charge carriers concentration, or you can write carrier concentration. So we have find out in, like in metals, basically a single charge carrier will be there, that is represented by N. So that single charge carrier N is representing the sigma, that is conductivity. This is conductivity. So conductivity sigma is NQ mu. Okay. So conductivity, uh, once we need to find out this carrier concentration. So this carrier concentration N can be given like sigma divided by Q into mu, and sigma is nothing but 1 by rho into Q into mu. So all these three value, once we know, by putting all these three value, we can find out the carrier concentration. Okay, so this is one of the way, another way that we can calculate the carrier concentration. Okay, so we will stop now. Yeah, if you have any questions, you can ask.